I want to talk a little bit now about the very basics of the energy state of water. Okay, so let's start with the simplest case possible, and that's going to be a glass of water. Okay? And we will put water into here. And we use this little triangle symbol to indicate where the water level is. And our first job is to identify a datum. What is a datum? A datum is our reference elevation. And we use that reference to identify the change in potential energy. Now keep in mind, if I hold this pen at this height and drop it, then what happened? Well, I turned potential energy into kinetic energy, right? Now, if I had held the pen here and dropped it, or if I'd held it here and dropped it, the rate of change of potential energy into kinetic energy would be the same. And what it is we always want to have a reference frame when we say this is where we're going to call zero potential energy. Any energy below this level will be negative potential energy, and energy above that level will be positive potential energy, right? So you have more energy above, less energy in potential energy below. So we will call this the datum. We typically use the letter Z for vertical elevation. And so we're going to say that here is where Z equals 0, okay? Now, the next thing we want to talk about is the water pressure. So that's the elevation, and that's going to be called the potential energy or gravitational potential. Gravitational potential. Okay. So now let's talk about pressure. So what we have here is at the top of this water, we have no water pressure in terms of water bearing down on us. So if we dove into this little glass of water, we'd find that our ears would not feel any compression when we just dove through the surface, but as we went deeper and deeper, we'd feel the pressure. So indeed, what we know is that in this system, we have what's called a hydrostatic. We have a hydrostatic system because the water's just sitting there. So the water is static, okay? So this is water. And this is still. Means there's no motion, okay? So hydrostatic. In a hydrostatic condition, then, we know that the pressure is, and this is going to be, I should draw this the other way, actually. I need to be a little bit more careful and draw this the other way. And what I'm going to say is this is going to be pressure, and this is going up. So this is going to be pressure equals 0. And the pressure at the top is 0. And the pressure as you go down increases. So that's a hydrostatic pressure profile. And what we know is that that pressure is equal to rho g h. Okay? And so if this is the depth of water h, And the density of water is rho, and we can put a W below it if you'd like. And then this is the gravitational pull of Earth. Then what we get is the pressure of water. And so what we immediately see is that we have two forms of energy. And we have elevational energy and we have pressure energy, or potentials. We would call these two potentials. Okay? So one of them is gravitational. And one of them is pressure. Gravitation, we indicate with a Z. Pressure, we're going to indicate with a P. And we will note that we can also say that P equals rho G H, or H equals P over rho G. And this, so in other words, pressure can be linearly related to elevation. And this we call the hydrostatic head. And the nice thing is it has units of meters. Units of length, we could say. But Z also has units of length. So what we often will do is work with hydrostatic head instead of pressure, because it's more convenient to have the same units in both of the two potential terms. Typically, what I use notationally is a capital H, which I'm going to call the total potential, and I'm going to say that that's equal to Z plus H. Okay? And so what I've done here is I've defined a potential which combines gravitational and pressure potential. It's going to have units of length. Okay? Now in this particular case, so if there is a difference in total potential, then what that'll do is that'll give rise to motion. So if I put if I take a plane of a board and I pour water on it and it sits still, but if I put an angle, there's a gradient of potential. It can go downhill and it will head downhill. So when the total potential is the same everywhere, then we have a hydrostatic case. So the hydrostatic case is specifically when H is equal to a constant everywhere in the system. What that means then is that Z plus little h is a constant. Then immediately what we can see is because we've decided that Z is equal to 0 here, then we're going to be able to say anywhere in this glass of water that the total potential H equals Z plus little h. And if we've assigned this to be 0 here, and this has a height of, let's say, L, for example, at the top, what's the value of Z? At the top, the value of Z equals L. And the pressure at the top, no water pressure. So little h equals 0. And so we can say for this datum, capital H at the top equals L. But if capital H equals L at the top, because this is hydrostatic, that means that the energy is the same everywhere, and so actually capital H equals L everywhere. Meaning at the bottom, where Z equals 0, what is the value of h, of little h here? Well, if h is equal to z plus little h, and that's equal to L, then if z equals 0, then little h equals big H equals L at the top. At the bottom, I'm sorry, at the bottom. Okay, so what we now know is the relationship in between total potential and elevation for a glass of water. Not maybe the most exciting discovery in science of late, but very, very important to understand the interplay between potential energy, which is higher as you go up, and pressure potential, which may increase or decrease. In this case, the hydrostatic potential pressure goes up as you go down, and the two taken together are a constant.